next up, this reaction name is ozonolysis. By adding ozone, break up in the middle, two sides, depending on the workout condition, oxidatively or reductively, two ways. Always ketone is same. If it goes reductively, it generates aldehyde. Oxidatively, it generates acid. It's quite given, huh? Permanganate is a super strong oxidizing agent. Break up everything and push to the end. Carboxylate. Carbon dioxide. It forms everything breakdown. It never happens stop in the aldehyde. Aldehyde can form clean but reductive conditions aldehyde. So it can form ketone, carboxyl acid. If there is a terminal stage CH2, then that generates the CO2. Iodide react with a dialcohol, 1,2-diprovisional dialcohol, and they can break up in the middle, generate aldehyde. Okay, epoxide protected by water removed and to generate the 1,2 type. Now, from now on, what direction? Okay, you don't know whether this is the E or G, depending on the priority. High atomic number determine which one is higher. But this addition is epoxide here, oxygen here, or attack from behind. And type. Okay. Syn is going together to the same side. This is from behind removed and type. That's the syn. Go together to the same side. Such as the syn on the metal surface equals to the same direction. 생각보다 연동이든 생각을 주고요. Okay, now we will go to alkyne triple bond. Okay, first of all, let's start with the name. Alkene case, we gave the name as alkene, octene, E, right? Ended with the T. Now, alkyne, triple bond, there it is then, it ends up with the extra ion. And position, same way, longest chain, and then the lowest number. And if there is any branch long, still containing this triple bond, longest one. Okay. And 1, 2, 3, 3 octine, or oct 3 ion, by the way. And position 1, 2, 3, 4, 6, 6 methyl, 3 octine. Position 1, 2, 3, beginning position. Very similar to the alkene. Right? Now, if we have both alkene and alkyne, we learned the double bond. Now we are learning triple bond. Then still you choose lowest number. Either here. So in this case, this is a triple bond here. But starting from here, there's one position. This is 1, 2 position. Then we choose the lowest number. In this case, if this is ion, ended with ion inside. So 4 methyl, 7 position this way, 7 non-in, 1 ion, and 4 methyl. In this case, maybe rather than this maybe looks like more systematic. Total length is 1 in, 9. 7 in, 1 ion. Looks like this is a little more systematic. That's why this is kind of needle suggestion. If the numbering is same position. Now in this case, this is 1. If it goes this way, this is 2. But if you cut off this, now here, this is 1, this is 1. If there is the same number, then interestingly, double bond wins. Final name we ended as triple bond, okay, ion, in ion. But if those two numbers is the same number, if it's different number, then we choose the lowest number. Okay, the double bond here, triple bond here, still, this is 1 position, this is 8 position. But if both of them are same number, 1 and 1, then gives higher priority to alkene. So in general, alkene double bond is more reactive than alkyne triple bond. So it gives some priority only for them. Okay. Now, if you use this as an alkyl group, this is alkyl, 4 carbon, that's a butyl group. Methyl, methyl, propyl, butyl. If it's a triple bond, rather than butyl, we call butane. And here's also position number, starting from here. Junction number here, 1, 2, 3, 4, so this is 1 to 10. If it's a triple bond, butynyl. And also give those number position number here. If this triple bond is here, what do we call? 2-butynyl. Okay, that's a 2-butynyl. If this double bond is here, what do we call? 3-butynyl. Okay, so this is simpler case. This is also allowed. Okay, of course we can make much more complicated situation about this level. Is what you need to know. Okay, more complicated one, giving name is not main issue. So important thing is the reaction. As we have just reviewed, similar reactions we can apply to alkyne. Compared to alkene. Alkene case, 1 pi electrons. Now alkyne has 2 pi electron, and those direction is 1 x. If this axis is the g axis, okay, 1 electron like this, x direction. The other pi electron is like this. 2 electrons are 1 here and 1 here. So it seems like they are protecting each other, so that's why reactivity is a little lower in general. Now, similar reaction we have seen. If there was alkene double bond, if you add the HB out, what happens? What's your product? If it's alkene. If it's a double bond here, what's your product? First reaction, pi electron is electron rich. There is a donated to proton, capture that, forming carbocation. And then Br minus bromide will come back and attack. And position wise, carbocation forms here, inside. And then product is Br here, H here. Is it Markovnikov or anti-Markovnikov? Markovnikov. Same reaction happens. One reaction, it goes Br here and H here. And except alkene is more reactive. then it may not stop. It keep going to the next step. BR is added one more here, and another BR coming here. Both of the reactions are Markov-Nikodym the way. And similar thing to HCl, HBr, HCl, similar way. Protonation happens first, and then Cr added. Now in this case, this position and this position is identical. Once this is formed, it may form here or here, but once this is formed, next step, Cl goes straight into this position because Cl is also a substituent. Okay? So and the product is this one. So reaction is very similar to double bond. So mechanism, similar way, capture proton, carbocation formed, and then Br minus come back, and then finish. Very similar mechanism. One pi electron donate to proton, carbocation, and then Br minus come. Similar reactions. So Br2. So let's review. Double bond, if it's an acid, then proton captured first. Carbocation is formed. Br2, Br can form bromonium by leaving bromide. So Br2 is added, then one Br is captured here first, bromonium intermediate, and bromide comes back and attack, and it is attacked from behind, ring open. It's a syn addition or anti addition? It's anti addition, similar to epoxide. Okay. Bromonium forms and Br minus an attack. That's why it forms this G form. So transform. And then next reaction again forms bromonium and then attack. So it can go further to make the whole bromine product. So reaction manner is very similar to alkene. So we have done HX and X2. Okay. Now hydration. Let's recall. In alkene case, hydration. If you have the acid and water, your product is adding water, 1 OH, 1 H. Selectivity. M or non-M? Markov or non-Markov? It's Markov. More substitute position was added because carbocation is formed there. Similar way, to alkyne, if you have the acid and water, and it gives OH like this. It's also Markov. Now, the next step is a little different. This is formed as an intermediate. Let's quickly rearrange to form this. What happened? This happened. So this one right now, we have seen this before when we studied something. So here is double bond left over, and hydroxyl is added here. This kind of structure we call is the alkenes in is alcohols or. This structure we call enol. And this is rearranged to form this. Electron movement, this pi electron is given here, and then this one is given here. And move to this form. What is the relationship between these two? Resonance, equilibrium. This is equilibrium. Okay. Why this is not resonance? This arrow means that this is equilibrium. The arrow can be drawn that way, or it can be drawn this way too. This way too. Okay, half a head. Both of them is acceptable. And this is a ketone. That's why this form is called as a ketone form. This is the enol form. The arrow implies that which one is more stable? Ketone form is more stable. Equilibrium just shifted to this way. Why this is not resonance? Hmm?
Because
Resonance form also looks like a different. The double bond position is changing. Sigma bond is sigma bond is different. Sometimes the resonance looks like also sigma bond. Sigma bond is there, but pi bond is moving. But here also pi bond is moving. New sigma bond to form the two. Any other simpler way to say? Atom was moved. Which atom was moved? Hydrogen was moved. Hydrogen was originally here. Now this hydrogen was moved to here. Now distance between this hydrogen and this hydrogen is changing. Atom position is changing. Okay. So that's the evidence that this is equilibrium. And among those atoms, hydrogen is the lightest. That's why hydrogen moving is the fastest. That's why when we saw those rearrangements of a carbocation, hydride shift was faster. alkyl shift was a little slower. Okay. Hydrogen is always faster because the lightest. That's why only hydrogen is moving in this kind of equilibrium we call tautomer. Only hydrogen is changing at the isomer we call tautomer. And this equilibrium we call tautomerization. Tautomerization. So that means the relationship between these two, they are isomers, not resonance structure. Because those structure looks like similar, but hydrogen position was moved to different form, but they can be very quickly back and forth. They can move. That's why this is kind of, it's not conformational isomer. Conformation is about rotation. This is definitely is a move, but only hydrogen is moved. This is faster to convert to each other than other isomers. That's why it is isomer, but it's a little close isomer or easily convertible isomer. That's why they gave separate name. These are tautomer. Tautomer is one kind of isomers. Only proton position, hydrogen position is changing. Okay. So this is possible. So let's go back. Now the first product is Markovnikov hydration product. Hydrogen added here, OH added here. Now this is kind of unstable isomer. Unstable tautomer, inner form. This form can quickly rearrange to form this keto form. So that is the product. How many water added there? In this reaction, how many bromine added? Two bromine was added, right? So one added and the second one also react together and two bromine was added. And in this case, only one water is added. Only one water added, and before it goes next step, if this goes another hydration, OH go here, and OH here. That should be the product. But before it moved there, this is rearranged quickly to form this. It's kind of a trapped and moved to different forms. Product, ketone. Double bond CO was formed. The position is not end position, it is an internal position. Because that's Markovnikov product. So very similar way, this reaction is acid catalyzed. In the laboratory, instead of an acid catalyst, what could you use to make it mild condition? To activate pi electron?
Yes.
Instead of an acid requires usually very high temperature. And what did you learn? Mercury, oxygen creation, right? So by adding mercury, similar things we can induce. So by adding mercury, the ion, this is Lewis acid, and it's capturing, forming this kind of intermediate, and then water added. oxygen creation. Oxygen cracking case, water and mercury goes together. Mercury activates and the water goes in. And we finish the reaction with reducing agent like sodium borohydride to remove mercury. Now here also, this inner form formed, and then this can be rearranged quickly to form the cyclic. Similarly, almost the same reaction, but instead of waxy, we could use the mercury ions, oxygen operations. Okay. Now we learned another reaction too, right? Oxygen operation gives Markov-Nikov product. We learned another condition. What is it? Hydroboration we learned, right? So on this reaction, if it is internal form, this can go either here or here. You may get a mixture. If it is a terminal, it goes oxygen go here. It forms this kind of ketone. In case of hydroboration, now if it is enter position here, pH2 goes here, H goes here because of a steady hindrance. H is bigger than hydrogen. That's why H goes to more hindered position. pH2 goes to more open positions. And then we replace that pH2 with oxidizing conditions. Then reaction happens on B side here, and then replace the B with the oxygen. Then the intermediate is formed. First intermediate will be, this will be formed. This inner form will be formed on the terminal position. And this can be rearranged quickly to form double bond. And that double bond is at the end position. That's why that's not ketone, that's an aldehyde. Okay. Similar way, if this triple bond is in the middle, anyway, it generates the ketones. Maybe mixture involved, similar to this. If boron can add here or here, it may generate the mixtures like this. If you design your reaction to generate this kind of mixture, that may not be good condition, good design. You don't want to have too many mixtures to purify. Maybe this is a better reactions. You can get only single product. So now you have two options. If you have a triple bond, especially terminal position, you have two options. Oxygen creation to get ketone, or hydroboration to get aldehyde. Okay. So this is the one step further from double bond reactions. Double bond case, where does the hydroxyl group goes? That's what we have studied. Now in triple bond, hydroxyl goes in and rearrange to generate CO double bond. That's what we have studied. This is maybe most complicated reaction we are going to learn today. So this is the quite, in a sense, simpler extension of alkene reaction. Now reduction. What did we learn? What did we learn for alkene reduction? What is the condition? 양현아, what did you learn? 갑자기 왜 눈들을 안 맞추고 눈들을 막 피하고 그래? In alkene, what kind of reduction reaction have we studied? Metal catalyzed. Is that hydration? Hydration is adding water. Hydrogenation. We added the hydrogen. To reduce the hydrogen on metal catalyst. That's what we have learned for reduction. Similar things we can do. So hydrogen and catalyst. So we can go one step to make alkene, and this can go further the next step. Now if you look at this reaction of the heat generation, which reaction is more exothermic? Which reaction generates more heat? First step or second step?
First.
First step.
Yes.
What does that mean? First step and second step, which step is more reactive? First step is the more reactive. Right? All other reactions, those addition of HX, Br2, those kind of things, alkene is more reactive, we said. Or at least all these hydrogenations. First step is faster. Second step is a little slower, maybe. Delta H is first step is much more stabilized, and second step a little less. So that means maybe it's possible to control those reactions. Okay, you can stop in the middle. In alkene case, to add this hydrogen, what is the manner? Syn or anti? It was a syn, right? On the metal surface, hydrogen activated syn additions. So if this reaction alkyne with good catalyst and H2, if you just push the reactions and both of those double bond, two double bond is reduced to form octane. But if you want to stop, now this catalyst may be too reactive. I said palladium is a good catalyst. Better catalyst is maybe platinum, more expensive platinum. But palladium is already good enough to reduce this to the end. Now we need to reduce the activity of catalyst by adding something like this, quinoline or lead. Now lead the acetate kind of reagent. This is kind of a poison of catalyst. Catalyst is still working, but with the reactivity is reduced catalyst. Developed by this scientist named as Lindelof. So Lindelof developed this catalyst by poisoning those palladium catalysts with some bad material to control those reactivity. If you reduce that the activity, then you can stop the reaction in the middle. And look at the structure of the product. Is it a syn product or anti-product? That's a syn product. Because the hydrogen will be added like this. It forms the cis product. Okay. Now you have two options. Starting from alkyne, you can stop the reaction in the middle, syn product. Okay, by Lindelof practice. If you add charcoal dispersed palladium powder, it can go further to the end positions. Okay. Here we have another interesting options. Palladium catalyst case, it's a catalyst. It doesn't participate in the reactions. It just helps to break up these two hydrogens. By adding those two hydrogen, which one is reduced? Carbon or hydrogen? Which one is reduced? Carbon is reduced. That's why we call this reaction as a reduction. Our interest is on organic molecule. What happened to the hydrogen?
Oxidation.
It's oxidized. H dot becomes H plus. Right? When the bind to carbon, oxidation number is a plus 1. It's more electropositive. Okay? In this case, reducing agent was hydrogen gas was a reducing agent because it is oxidized. Okay? We call this a reduction reaction because there is electron movement happened. Now, this is also reduction. Now, if you look at those conditions, you can guess which one is reductant. Which is reductant? Lithium, metal powder. Metal itself is reductant always. How? It donates 1 electron. Lithium can donate 1 electron. Calcium can donate 2 electrons. Magnesium 2 electrons. Sodium 1 electron. Okay. That electron donation happens in cold solvent, perfect solvent. Water freeze at 0 degree. So for low temperature, we cannot use water. Ammonia can go much lower temperature in liquid state, and it dissolves those metal. So we call this as dissolving metal. Slowly dissolve in and donate that electron to this bond. And this double bond, pi bond, the electron rich. It's ready to accept electron rich, but still that's a little different. So this bond can accept that electron and make a couple ready to react with the product. So then product is electron was donated, and then proton was captured by that. Electron was donated, it forms a negative charge here, and it can catch this proton to finish up these reactions. If you look at this, the product, what's the difference from hydrogenation?
Not seen.
Say again.
Not seen.
Okay, this is a trans product because this reaction happens step by step. First step, lithium donate one electron, forms carbocation here, and they can capture one proton, one reaction done. And the other position is still open as a radical, and capture another electron. And now it has a chance to form this either cis or trans. Energetically, cis product and trans product, which is more stable? Trans is more stable because the cis has a stability here. Trans is more stable. Hydrogenation case, hydrogen was added at the same time. That's why there was no options. It's added to the same side, it forms the cis product. But this reaction is step by step. One electron was donated, and after some time, and the second electron was donated. So it has a time to build to find the more stable forms. That's why the product is formed as trans product. So this is an important point. If the reaction happens together, it's controlled to get only one product, syn addition. If it is step by step going in, then more stable form can be formed. So reduction, we have second, the method that we can see. So in alkene case, this reaction doesn't happen, so that's why we didn't run this. Alkyne case, if you add lithium reducing agent, and we didn't give a hydrogen gas here. We just donated the proton, like water, ammonia. Okay? H plus is already stabilized one. Reducing agent was metal. And at the end of the reaction, lithium becomes what? Lithium zero becomes lithium plus. It's oxidized. Okay? So reducing and proton capture happen to generate this product. So two reaction conditions we got. Syn addition and step by step trans product. Lithium dissolving metal. Okay. Permanganate. Now we are going to the oxidation. We learned the several conditions for the oxidation for alkene. Alkene case more versatile, ozonolysis, and what else did we learn? Permanganate, and what else? 4SO4, osmium tetroxide to generate to 1,2-diol. Alkyne case, not much reactions that we usually utilize, but strongest permanganate. Then it breaks up everything and push that to the end position, to the acid. It doesn't stop in the middle. Same product we could get from alkene. If it's a mild reductive condition, it could generate the aldehyde, but permanganate to break up everything to the end. And if it's an end position, it will forms carbon dioxide. First product is the formic acid and further oxidized to form carbon dioxide. Okay. In a sense, it's simpler. Permanganate is a super strong particle. Okay. Acidity. Acidity means it's the ability to generate a proton. Now, alkene or alkane, we don't have this kind of acidic proton. Alkyne, this end position of a proton is slightly acidic. And then it can be removed by strong base. Here, this is generated by NH2 minus, is generated from deprotonation of ammonia. Then this is ammonia. NH4 is ammonium. This NH2 minus, what do you call? Ammonia, ammonium, ammonite. Yeah, ammonite is a good option. In this case, amine ammonium, this is ammonite. So NH2 is called as a class. Ammonite is also can be used, but as a class, we call this ammonite. NH2 minus is a very strong base, and it can capture this proton, generate this carbon anion. Now in this ammonia, the pKa is about 35. Acid-base reaction happens even though it's a weak acid. If there is a stronger base, then it can remove the proton. Okay. So if you compare alkyl and double bond sp2 and triple bond ESP, further and further, S character, this is about a half. This is about 1/3. This is about 25%. S character is becoming bigger and bigger. That means S character has a more electron attracting the character it has. That's why if it forms an anion, that anion can be better stabilized than the other two. That's why those acidities can be defined whether the generated conjugate base is stable or not. So by looking at those pKa, super weak acid. This is also weak acid, and this one is still weak acid, but still better than the other two. And this pKa of alkyne is 25. What is the pKa of ammonia? What's it? 35. That is bigger than this, and then lower than this. That's why amide cannot deprotonate this. Amide can deprotonate this. Okay. There are many variations, but this is one reaction. It's listed here. Triple bond, terminal triple bond, it can be deprotonated, and it can generate amide. So it can generate carbanion. Carbanion is a good nucleophile. Good nucleophile. And this electron-rich species, intermediate is formed, and it is looking for electron-poor species. As here. Bromide is more electronegative, so delta minus forms here, and then this carbon forms delta plus. That's electron-poor position. And this electron-rich position attack this carbon, and from behind, and then push this out. And this coupling happens like this. This was added, and then this NaBl is as a other side of product. This reaction now, if you look at this structure, methyl bromide, alkyl halide. That's what you have to study seriously from next week. And this reaction we call SN2 reaction. So that's also what we're going to learn next week and the next week. So 2 weeks. So it's just the beginning of to give you some taste. Electron-rich species, carbanion, electron-rich. Typical good nucleophile. React with the alkyl halide. Typical good electrophile. And generate this kind of carbon-carbon bond formation. So this is just one example that we just see. So the reaction here, now the bond of the approaching direction is, this goes on the same line of this bond, go from the behind, and the attack here, and then this is the transition state. Transition state is a planar structure. And then this is inverted to the other side. If you think about it, this is like umbrella. Umbrella is inverted to the other side, like this. That means stereochemistry on this position can be inverted. Originally, the S state is the R form, product can be S form. Okay. So that is a serious review to study next week. Today, just one example you see. Okay. Good nucleophile generated by deprotonation of alkyne. So that reaction, as we just said, amide, sodium amide, the other protons are too weak. We cannot remove them. Only terminal alkyne. This is pKa 25. This is pKa 35. It's a stronger base. It can capture minus atoms. And alkyl bromide. And attack is one attack here from behind. Remove this bromide. And this is the drug. We are learning organic chemistry. Organic chemistry handles carbon-based molecule. That's why making local carbon means carbon-carbon connection is key reactions. Okay? This is one of those key reactions, utilizing carbon anion and attack alkyl halide and connecting carbon to carbon. Make short to long carbon molecules. Now, this reaction, if it is accepted, both sides terminal. Then one reaction, remove one, can react two product to generate this product. And if it's terminal, that means that this can go to the second reaction too, because it is another acidic proton. Then remove that and then go to the second one. If you control the amount of reagent, so this is R prime, implying that the different molecule. So it's possible to add one here, add the other one here. It's also possible. So we learned one reaction, then we can think about how to utilize this. Okay. So let's just say this is our target molecule. And it's suggested that this is your starting materials. It's a terminal alkyne and alkyl halide. It seems like they are asking us to do some SN2 reactions, nucleophilic additions. But this is the product. And this double arrow means this is not single step, this is multiple step. Maybe 2 steps or 3 steps. Okay. So let's think how to make this from these reactions. First reaction, if we attack here, we can get triple bond product. Deprotonate this, and then this attack this position, add it here. Still, it's a triple bond, and we need a one more step reaction. What reaction do we need? By looking at the structure. What condition do you need? It's a syn addition. What is the reaction condition? Mercury. It's an oxymercuration. Oxymercuration was a hydration reaction. So that's not H2 and what catalyst? Metal, palladium, charcoal. If you use the palladium charcoal, what happens? It goes to the alkane, right? Fully saturated Lindbergh catalyst. So if this is the reaction, then we can start thinking from the final product to go to the one step back. One step back, that's a triple bond, right? Then triple bond, maybe starting from the triple bond, and Lindbergh catalyst, and hydrogenation, syn addition. If you wanted to get anti-addition product, trans one, then what condition should we use? 배웠잖아. 그래서 what condition do we need? If it is an anti-product we want to get, lithium in ammonia. Okay, that's a dissolving metal condition. Lithium in ammonia. Lithium dissolved in ammonia. Then slowly it donates the electron one by one. It forms the transit product. So this is the last step. Then we need to make this. Then from this alkyl group, to make this, then what alkyl group do we need to use? Methyl bromide or methyl iodide. So next week we are going to see methyl chloride, methyl bromide, methyl iodide, which is better kind of thing we are going to learn. Anyway, for now, methyl bromide. Then the process is dissolving metal, and then to generate this carbon anion, and then here methyl iodide, bromide, anything more. Then attack here, then generate this. 2 step reactions. All together, starting position was the terminal alkyne, deprotonate using sodium bromide, and then react with the methyl halide, and by adding this methyl group. Okay? And then Lindbergh catalyst, hydrogenation. So make this product. Makes sense, right?
Yes.
Now you feel I can do anything. So this kind of analysis, you have your target molecule, and then you need to make this, starting from simpler structures. Then you need to analyze this from target. It's easier to break this down and then make it smaller and smaller. That kind of analysis we call retrosynthetic analysis. Retro means backward. Okay. So synthesis should be from small to complicated one. So this is final product, complicated one. Break down one by one, moving backward. That's what we call retrosynthetic analysis. So let's try it. Now this is your target molecule. It just suggests that your very starting material is acetylene and antialkyl. Okay, make this. So last molecule, how will you break down this? Bromide addition. Today we have learned to add one bromide. Then what is the precursor of the reaction? To make a bromide, add bromine Br2.
Yes.
If you add Br2, usually you get the 2 bromide, HBr, or HBr is maybe too reactive. Oh, sorry, HBr is fine. HBr, then what can be your precursor? Alkene. Alkene has 2 options maybe. HBr is fine, but alkene is this one and this one. You have 2 options. Which is the better option? Upper one? Because it forms only one product here, right? It's a Markov-Nikov product you will get.
Yes.
If you use this one, you will get mixture, this one and this one.
Yes.
And you should purify.
Yes.
It may form half and half. It's not good design. Okay? So this is bad. Okay, this one maybe you could use for the last step. Now then, how could you make this? The next question. Starting material was here. Starting from the acetylene. And you need to make this. Propyl bromide, maybe break here. Then this is acetylene motif, and this one maybe. To do that, you need to make this double bond, triple bond first, right?
Yes.
So to make a triple bond again, if this is, it doesn't say cis or trans. So in this case, you can choose either one. If your product is defined, then you should choose one. But if this is just a triple bond, double bond, then we don't know if this is cis or trans. So you can choose either indolocalist or lithium in ammonia condition. So this is your one step further. Now this from acetylene, now this is propyl. Propyl bromide. So here propyl bromide and acetylene plus sodium iodide. Deprotonate this, make carboanion, and then attack one of them, attack with this, then bromide is removed, and then forming this. And then next step, the catalyst or lithium in ammonia. And last step is bromine addition, HBr addition.
Yes.
That's correct. So first step, deprotonate, alkylation, and with the catalyst double bond, and you will get the cis product. And then actually it doesn't matter in any cases. So this is also HH. So and the two reactions gives you the same product. There is no second chance. And HBr, then BRZ. Okay, now we can design multi-step reactions. Let's start one. Okay, how will you make this? Reaction condition is also same. Acetylene and alkyl halide. And this is your your final product. How do you make it? Now it's a hydroxy.
Yes.
Then that's a hydration reaction.
without.
We didn't learn many reactions. We learned so far double bond react with the different things,
Oxygen creation.
and oximer creation is also one of the conditions. Hydration reaction or hydroboration reaction to control the position of the hydroxide addition. Okay. So those are some reactions we have learned. Now, by looking at the end product here, utilizing those reactions we have learned.
Hydrogenation.
So hydroboration that we can do. To do that, we need to have double bond here,
Yes.
right? And double bond was set the problem suggested. We start with the acetylene triple bond.
Yes.
Then the last step may be hydroboration and oxidative workup. Then we can get this. Now this one is double bond. Making linkage here, double bond, we cannot deprotonate. That's why we need to generate the triple bond.
Yes.
Triple bond should make this. What condition? Lindlar catalyst or lithium in ammonia. The same product we can get. So Lindlar catalyst we can generate this. Now this one, how to make it? Acetylene and a little bigger, but this is a whole chunk. If this is too big, maybe we need to break down somewhere or two to make it even smaller. Let's see. Starting from acetylene, if we can buy this, then this can affect this and generate this. So it didn't request further. If this is also very complicated field, we need to break down the two. So this is the summary. Starting from acetylene, sodium amide, deprotonate,
Yes.
and then alkyl halide and Lindlar catalyst, partially reduce, or lithium in ammonia, which also works. And then last step, hydroboration and oxidative workup. Okay. And we form this one. So during the next 2 weeks, we are going to study alkyl halide reaction with the nucleophile. Depending on the conditions, it may generate a different product. That's a little further sophisticated reactions, but that's kind of a core reaction in organic chemistry. So this is still kind of warming up. We only focus on double bond characters. Double bond as electron donor nucleophile. It can be oxidized to form epoxide, reduced to form hydrogen capturing, hydrogenation, or hydration reaction. Hydration is not oxidation or reduction. One reduced, one oxidized, that's why it's the same. H reduced, OH oxidized. So it's not oxidation or reduction. Okay? That kind of reaction we learned so far. And today, triple bond, and unique property is this is the acidic proton. We can remove it to make carboanion. So this is the first time we see carboanion. So far we talked about the carbocation. Carbocation structure, planar structure. Can be attacked here or here, same side. Carboanion, what do you think? Structure of that carbon position? Trigonal, planar, or tetrahedral? Planar? Tetrahedral? It should be tetrahedral. That electron is electron rich part. It forms one position similar to ammonia.
Yes.
That position is ready to attack electron poor positions. Okay, that reaction we have learned. Okay, we are here now. Alkyne, and then next week we are going to study alkyl halide and alkyl halide reactions. SN2, SN1, E1, E2, kind of different mechanism chemistry. This is what you're going to learn until this semester, and then analysis method. Okay, so just 2 more weeks to go. This week, we have the class next Tuesday. What happens on this Thursday? We have a Korean Chemical Society meeting this week. So I give you small assignment. So I gave on the PLMS how to read the number, size, concentration. There is a small other question set there. So go there, and this Saturday we don't have a class here. You study on your own by studying that material, and there is a small assignment there. Okay. So same due date until next Tuesday, and try to solve those problems and study yourself.
Yes.
Okay. So after here, any question? 자, 시간이 조금 남았을 때 미리 오늘까지 공부했던 거 you have time to review what you've studied so far, and then be ready for next revisions. Many more reactions will come, so it's better to summarize what you've learned so far. Okay, then see you next week.